is to provide vibrational information to the engine control module. This allows the ECM to limit the maximum ignition advance. They protect the engine from harmful knock or pre-detonation. Detonation is known by different names, such as pinking, knocking, spark knock, and pre-ignition. The noise that is normally associated by knock almost sounds like rustling coins in your pocket, or more severe cases would seem as though ball bearings are bouncing on a tin roof. Knock may be caused by several different operating conditions. The ignition timing could be too far advanced, the outside air temp could be high with an increased engine load, or it may even be caused by poor fuel quality. Excess carbon deposits located within the combustion chamber act like glow plugs. This will result in pre-ignition or two flame fronts colliding on the compression stroke, one from the ignition event and the other from the glowing carbon. The increased heat creates a rise in cylinder pressure, resulting in higher engine temperature. The cooling system struggles to remove the added heat and damage to the engine components may occur. Using a knock sensor as part of the ECM's ignition strategy allows for correction of ignition timing and injection duration, preventing harmful detonation. A knock sensor, in its simplest form, converts vibration to an AC voltage signal. The signal is sent to the ECM where it's conditioned and amplified. This is made possible due to the piezoelectric sensing element. The amplitude and frequency of the signal will depend on the level of knock detected. If a knock is detected, then the ECM will retard the ignition timing by a programmed amount. Once the knock is no longer detected, then the timing will be returned to normal in small increments at programmed intervals. The ECM has pre-programmed knock values. It will know the difference between normal engine noise, a pre-ignition event, a misfire, or even a noisy power steering pump. The knock sensor is threaded into the engine cylinder head, block, or intake manifold. Many engines now utilise two knock sensors spaced evenly along the engine block. The knock sensors are allocated to cylinder groups for accurate noise detection. This greatly enhances the detonation control. In a CRD engine, this allows the ECM to adjust the injection quantity for individual cylinders depending on the level of knock. In conjunction with the knock sensor, the ECM will also use the crank angle sensor data to determine the optimal injection duration. If a fault exists within the knock sensor circuit, the ECM will set a fault code. P0328 and P0333 indicate the signal voltage on these circuits has exceeded a predetermined level. These codes will be stored when either bank 1 or bank 2 knock sensor is shorted to voltage or an open has occurred. Remember to always use a battery maintainer when diagnosing any voltage critical circuit. Use a scan tool to inspect the freeze frame data. This can be used to assist in reproducing the fault. Freeze frame data is invaluable when it's time to diagnose a knock sensor related DTC. Knowing the engine's temperature, how long the drive time was, and the ignition timing values at the time of the failure can eliminate the guesswork. With the scan tool connected, start the vehicle and monitor the live engine data. Use a soft face hammer, tap the engine's block, cylinder head or intake manifold. Inspect the ignition timing data for any alterations in spark advance. If the vibration was detected on the scan tool, the ignition timing would have been seen to decrease momentarily. We can now confidently say that the sensor and the associated circuits are in a serviceable condition. Another way to determine the knock sensor's circuit integrity is by using an oscilloscope. With the engine off and back probing the knock sensor at the ECM connector, tap the cylinder head, block, or inlet manifold with a soft face hammer. A correctly operating knock sensor and circuit will look like this. But this is testing the circuit with the ignition off, so a shorter voltage may not register on the scope. Turn the ignition on and repeat the test. A shorter voltage in the circuit would look like this. To isolate the faulty circuit, we'll now need to use a digital multimeter. Referring to the vehicle's knock sensor schematic, we can see the circuit is monitored via a pull-up resistor and a ground is supplied by the ECM. The voltage available at the monitored pull-up circuit must be significantly lower than 5 volts. This is because the ECM would not be able to detect a short from the high reference circuit if the monitor point was held at 5 volts. With the ignition in the off position, disconnect the knock sensor. Place the meter on volts and connect the black lead to battery negative and the red lead to the monitored circuit of the knock sensor connector. Turn the ignition on. We should see significantly less than 5 volts. If a reading of 5 volts or over was displayed, then there is a short to voltage within the circuit. To determine if the fault lies in the harness, turn the ignition off and disconnect the ECM connector. Turn the ignition back on and monitor the display. If the voltage was still seen, then the fault is within the harness between the two connectors. If the voltage disappears, then the fault is within the ECM or a circuit from the ECM. To isolate the short, perform a continuity test between the monitored circuit terminal and every other terminal within the ECM connector. If this checks out okay, then the short to voltage must be within the ECM. With the ignition on and the meter connected between the monitored circuit terminal of the knock sensor connector and battery negative, we should see significantly less than 5 volts. If a reading of 0 was displayed, then there may be an open within the circuit. To quickly confirm this, move the black meter lead to the positive battery post. This will rule out a short to ground. If the meter still displayed 0, then we have confirmed the open. Move the black meter lead back to the negative post and with the other, back probe the ECM monitored circuit terminal and watch the display. If the correct voltage is now seen, then the open is between the sensor and the ECM connector. If voltage still isn't seen, turn the ignition off and disconnect the ECM connector. Check for terminal retention and corrosion. If this is deemed to be okay, then the open is within the ECM. Knock sensors are available in dual or single wire configurations. In a 2-wire circuit, the ground is supplied by the ECM. In a single wire knock sensor, the block or the mating surface acts as the ground. An open in either type of ground circuit will cause a signal voltage high DTC. It's imperative to check that the sensor is tight and all contacting surfaces are clean and free from corrosion. In a dual wire knock sensor, an open should be diagnosed with a multimeter. With the sensor disconnected, attach the black meter lead to the low reference terminal and the other lead to battery positive. Battery voltage should be seen. A reading of 0 volts would indicate an open in the low reference circuit. Move the meter lead to the ECM connector and back probe the low reference terminal. Battery voltage should be displayed. If voltage is seen, then there is an open between the knock sensor and the ECM connectors. If no voltage is displayed, turn the ignition off and disconnect the ECM. Check for terminal retention and that no corrosion is visible. If no fault is found, the open is within the ECM. If we have proved that the knock sensor's circuits are okay, then the only possible fault will be the sensor itself. Well, that concludes diagnosis of a knock sensor signal voltage high DTC. Consistent training will ensure you keep ahead of the game. Thanks for watching. See you soon.